Hello everyone, my name is Debarshi Chatterjee and today we're going to discuss how to solve n cross n tic-tac-toe problem using system Verilog constraints. The 3x3 version of this problem is a very common interview question, but in order to make it more fun, we're just going to solve the more general version of this problem, which is the n cross n version. So in the game of tic-tac-toe, two players play alternately on an n cross n board, which is typically a 3x3 board. And players would put cross or circle on the board alternately, and until one of the player wins, or there is a draw game, or one of the player quits. So what constitutes a win? A win is when a player playing cross would win if he is the first person to place cross across at least one direction of a row, column, or diagonal, or a reverse diagonal. A draw game is when both players have put all their marks on the board and neither of them has win. And a quit game is there will be nobody wins and there is no draw, but there are empty places in the board. So this is similar to one guy quitting in the middle. Let's now take a look at a legal board game and an illegal board game. So the board game on top is a legal board game because let's say the player one started putting a cross and he put this one first. Then the player two made the second move, and the player one made the third move. Player two made the fourth move, and this guy made the fifth move, and so the player one won. So it seems this is a legal board game. And the second one is an illegal board game because since the players are playing alternately, there is no way that the difference in number of moves for the player 2 and 1 will be 3. So hopefully we understand the problem now, and then we have to write system Verilog constraints to generate legal board games. So before we get into the solution, let me just mention that there are different ways of solving the problem. In any solution, accuracy is of prime importance. So what that means is that in order to generate legal boards, we should not over-constrain it. In that case, it will generate all legal boards, but it will miss out on boards, some legal boards, and that is not good. Similarly, under-constraining is not good, which is generating illegal boards. So in this method, we're going to also talk about scalability and flexibility. That is, we want to generate a method which is scalable so that as n grows for any arbitrary board size, we can scale this method up. And flexibility means we can generate legal board outcomes biasing towards a certain case. For example, we want to say 80% draw cases we want to generate. So we should have some flexibility in that. Some other considerations are performance and conciseness for system Verilog constraints. And so that being said, let's dive into the solution. Okay, let's now discuss a constraint which will be true no matter what the outcome of the game is. And that constraint emerges from alternate play. So the absolute value of the differences of the moves made by player 1 and player 2 must be less than or equal to 1. And we will see here that while this is a necessary condition, it is not sufficient. And this is shown by two examples here. In both of these examples, the differences of the moves made by the two players are either 0 or -1, which satisfies this equation, but none of these are actually legal game. And the reason being, in the first case, there are two winners, and this is not possible. When one guy wins, the game stops and the other guy cannot play. And the second is illegal because the winning guy's number of moves is less than the losing guy. This is also not legal. So while this is a necessary constraint, it's not a sufficient one. To generate sufficient conditions, we have to kind of enumerate the possible different ways or outcomes of the game and then write some constraints based on the outcome of the game. So we'll see that in the next slide. Let's now enumerate the outcomes of the game. So to write the constraints, we have to first see what are the outcomes of the game. So at the top level, we could randomize this single bit variable, which can be either 1 or 0. If it's 1, we will know that we are generating the board for a winning game. If it's 0, we will generate the board for a no-win game. But now in an n-cross board, in general, a winning can come from either one direction, 2 direction, 3 direction, or 4 directions. And these directions are row, column, diagonal, or reverse diagonal, right? So in an n cross n board, there are n rows, n columns, one diagonal, and one reverse diagonal. So if you add them up, you will see that the single direction win can come in 2n plus 2 ways. And so a player 1 can win in a single 1D game in 2n plus 2 ways. Player 2 can also win in 2n plus 2 ways. And okay, now we're going to take a look at what we mean by a 2D win. Okay, let's now try to understand what we mean by a 2D win in a 3x3 context, and then we will expand that, generalize that for n cross n board. So let's say this is a 3x3 board, and the first player plays with a cross, second player plays with circle, then we have cross, circle, cross, circle, cross, circle, and the first player plays the final moves, and when he plays the final moves, he wins in two directions. Now, this is what we call a 2D win. The thing to understand here that the 2D win needs to have a common intersection point. And here, as before, we have the different directions are row, column, diagonal, and reverse diagonal. And there are n rows, n column, one diagonal, and one reverse diagonal. And so we cannot, in order to get the common intersection point for a 2D win, we cannot select two rows. We cannot select two diagonals. Basically, parallel direction cannot be selected. And if you select any two non-parallel directions, there will always be a point of intersection. So let's now enumerate what was the different number of ways in which 2D win can happen in an n cross n board game. It can happen if you select one row and one column, which you can do that in n squared ways. You can do row and diagonal, which can happen in n ways. That is row and diagonal here n times 1 n ways. Similarly, you can do row and reverse diagonal, and that can happen in other n ways. You can do column and diagonal, that can happen in n ways. You can do column and reverse diagonal, that can happen in other ways. And finally, you can do diagonal, reverse diagonal, which can happen in one way. So if you add them up in an n cross n board game, you can see that n squared plus 4n plus 1, that's the number of ways in which a 2D win can happen. So for writing the constraints, we don't need this enumeration, but this is just for fun. The key thing to remember here is that for a 2D win, we need to just select, we need to write constraints so that these two wins that we select are not in the same row, are not, both are not belonging to rows, or both not belonging to columns, and so on. And we will see how we can write those constraints. But this is about 2D wins in n cross n board games and its enumeration. Let's now look at 3D wins, and this is probably the most complex. The 4D win is much easier. So the 3D win case, like the 2D win case, happens when the winning player makes the last move, and in the last move of the win, he wins across three directions. So this three directions could be column, row, and diagonal, or column, row, and reverse diagonal, and so on. So 3D win can happen across column, row, diagonal, or column, row, reverse diagonal, or column, diagonal, reverse diagonal, or row, diagonal, and reverse diagonal. So so column, row, so the complication over 2D win is that in 2D wins, we see any two non-parallel direction, they will always have a point of intersection. But in this case, in order for these three directions to meet at a common point of intersection, we have to write additional constraints. So let's take a look at the first one. So column, row, diagonal. In order for column, row, and diagonal to have a common point of intersection, basically the column and the row number must be the same, and then it's guaranteed to intersect at the diagonal. So for an n by n board game, the column equal row, there are n possibilities. So this case can be n ways. And this case similarly can be n ways. Then we have the column diagonal and reverse diagonal, and row diagonal, reverse diagonal. So diagonal and these two cases can only happen in an odd board game, and um, if if it happens, then there is only one way this can happen, and then there is only one way this can happen as well. So the overall number of 3D wins is 2n plus 2 if it's odd, if n is if n is even. Sorry, 2n plus 2 if n is odd, and 2n if n is even. Um, it is also worth mentioning here that for a certain n, smaller n's like n3, this 3D win cannot happen. So in order for the 3D win to happen, at least you need n5 and so on. So that's about 3D wins. And next, we are going to discuss about 4D wins. So how do we write constraints? So if you look at the solution, I have written constraints to make sure that in case of 3D wins, we first decide which of these cases, row, column, diagonal, row, column, reverse diagonal is happening, and then we have to make sure that we constrain the point of intersection so that these row, column, diagonal have a common point of intersection. So 4D win cases are much simpler because like 3D win, we also need we need to have a common point of intersection for the four things. So if the n is even, then there is no position in the board which has a common point of intersection between the diagonal and the reverse diagonal. So like before, for n is even, the 4D win cannot happen. But if n is odd, then there is a common intersection of the diagonal and reverse diagonal, and in the number, the row and column in which it happens is n minus 1 over 2. And so there is exactly one case of 4D win in if n is odd, and the number of 4D win is n is even is 0. And again, like before, 3 cross 3 cannot have 4D wins, so a number of 4D wins starts happening at a higher number of n. Yeah, that's pretty much about 4D wins. So other part of the subtree, that is when win is 0, is simple. We get a no-win game, and the no-win game, we can randomize another bit to decide whether we are doing a draw game or a non-draw game. If there is a draw game, basically all we have to make sure is that there are no wins, and basically no place in the board is empty. And if it's not a draw game, then it's an incomplete game. The only constraint there is, again, there has to be no win, and then there has to be at least one empty position in the board. So now that we know all the different outcomes, let's see how we can encode the problem and write constraints for all of these conditions. Let's now see how we can write the general constraints for a winning game. So before getting to a winning game, we had two variables. Remember that the topmost decision variable was a win, 0 or 1, which was a bit, and we randomized. Once we know that win is 1, then we randomly select an integer based on 1, 2, 3, 4. Again, the exact coding is there in the solution. You can take a look, but I'm just trying to explain the high-level idea here. So once we know it's a win, we decide solve before before we solve P1 wins and P2 wins. So P1 wins and P2 wins are basically 2n plus 2, a bit vector with 2n plus 2 bits. Each of P1 wins is a bit vector of 2n plus 2, and similarly P2 win. So the first thing is, first constraint we have to write is that is to make sure only one player wins. And this is the constraint that does. So count once, P1 wins equal to win D. So that player can win in different directions, but either they have to come from P1 wins or they have to come from P2 wins. And if one of them is, this constraint basically makes sure that there are no two winners. And you cannot have two parallel directions as a winning direction. So you cannot select two rows. So that this is saying that, and this is saying you can have two columns in the winning direction. And finally, there is some constraint based on the board, sum of the board. So this is emerging from the fact that the winning player will have to, the number of moves made by the winning player is always greater than or equal to the losing player. And this is because when a player is in general making a move, his move has to be, prior to making the move, his number of moves has to be less than or equal to the other player. And because the win can happen only on the final move, after the winning move, the number of moves by the winning player always have to be greater than or equal to the losing player. So those are written here. So in this slide, I'm showing subset of the constraints that we wrote in the real solution. There are some additional constraints for 3D and 4D winning case to constrain the intersection point that I explained earlier. But this is how overall the constraints of the winning game would look like. So the constraints for a draw game and an incomplete game at the are, one of the constraints is same. If the winning game is 0, then it could be a draw game or an incomplete game, and in that case, count ones of P1 wins and P2 wins is equal to 0, basically saying that there are no wins. And then the additional constraint is that the draw game, the empty sum, the sum of the empty marks on the board is 0. We will, in the solution, you'll see how we define empty sum and so on. So for the incomplete game, it's same as the draw game, that there should be count ones of P1 wins plus P2 wins is 0, means there are no wins in the game. And in an incomplete game, the empty sum, the sum, that is the sum of empty numbers in the board, has to be greater than 0. Finally, let's take a look at the board encodings. To print out the board, we create this rand int n by n tic-tac, and the encodings are as follows. The player 1, if player 1 marks a cross in a certain location, we will put a 1 in the board, and if player 2 marked a circle, we will put a -1 in the board. And we have additional variables, rand int, row sum, column sum, and we'll write constraints so that this variable here is the sum of all the row elements and so on. Similarly, for column sum, every element here is sum of the columns in the tic-tac. And we'll also have random variable rdag sum and dag sum. And the reason for choosing this encoding is that remember that P1 wins bit vector. So we will write constraints between this and the P1 wins. And if there are n1 on the board across a row, then the row sum for that will be n, and then we will know that P1 has 1 in that direction. The last step is to write leaf level constraints, which basically constrain the row sum and based on the P1 wins. So in this code, what it means here is that if there are n crosses across a particular row, then P1 wins in that row. And if P1 wins in that row, it's a bidirectional constraint. Similarly for columns, diagonals, and reverse diagonals. I think I tried to explain the overall process of the solution, but let's now take a final look at the code in the EDA playground, and let's see how it works. Okay, so let's now go over the final solution in which I tested out on EDA playground. As I explained in the slide before, the topmost decision variable is a winning game. And this is solved before every other variable. The second level decision variables in the decision tree are draw game, incomplete game, and the win directions. Once we decide which way it's going, let's say if we have win direction is 1 or 2, the third level decision variables are P1 wins or P2 wins, which are 2n plus 2 bit vectors corresponding to 2n plus 2 directions in which P1 could win, or 2n plus 2 directions in which P2 can win. Then we have these variables tic-tac n cross n. This is the board, and this is the transpose of the board, which is needed for calculation of the column sum. And then we have the row sum, column sum, vectors, and yeah, so these are the final level variables. So at the top level decision variable we solve before everything else, we assign it some distribution. The second level draw game, windy and incomplete game need to be solved before the lower level decision variable. We also assign those variables some distribution probability, and we write the constraints between the second level decision variables. For example, that if it's a winning game, then it cannot be a draw game and vice versa and things like that. Now coming to the third level decision variables, which are P1 wins and P2 wins. So based on what the windy is, we write constraints on how the P1 wins and P2 wins will be with respect to windy. And I explained this in the slides that win can come only from one of the players, and that the winning directions, one player can win in multiple directions, but those directions cannot be in the rows, in two rows or in two columns. And so that those are general winning constraints. For 3D wins and 4D wins, some constraints, because the row column diagonal, row column reverse diagonal, etc. have to have a common point of intersection. So this is the code for that. Similarly, for 4D win, there's a intersection related code. And finally, the board lower level code is the constraint involving the board with and calculating the number of crosses and empty spaces and circles in the board. So that's the code here. And these constraints here say that if there are n crosses across a row, then P1 wins in that row and vice versa, similarly for columns and so on. So you can go over the solution. Let me just run this code and show that this at a high level works at n equal 3. So let's run the code. So here we see for the 3x3 board, it randomly printed out a winning game. And here P1 wins, and P1 wins means the cross wins across the diagonal. And the next is also a winning game. Here also P1 wins, and the winning direction is 2. So that is, it shows this diagonal and this column. Let's see. So again, another winning game, 1D winning game, 1D winning game. Yeah, so here it didn't print out a draw game, but let's make a constraint here. And oh, actually I was running with winning game, so maybe I should remove this. So if we just run this, now we should see some draw games here. If not, let's make a draw game and see if it can get some draw games for us. Okay, so this, yeah, see, it's 3x3 draw games, no empty space, and you can check that nobody wins in each of these games. Similarly, we can constrain it to generate incomplete games. And let's run it to see. So this is what I meant by flexibility, that you write a code in such a way that you can generate all these different types of games. So here, this is an incomplete game. There are no marks, and you'll see there are no winners in any of these games. So those are incomplete games. So we made the code flexible enough to kind of generate all these different types of games: winning game, draw game, incomplete game, and then different types of win directions. Now, finally, let's also see if this code is scalable. So we change the n to 5, and now let's say for a 5x5 game, let's try to generate some winning game. And let's see what that prints out. So here, this is a 5x5, and this is a winning game, and it's a 1D winning game. And who wins? P1 wins. So P1 means cross wins in one direction. So this is the 1D. Then this is a 2D winning game. Here P1 wins again, and P1 wins in this row and column, right? And then Again, here are 2D winning games. Here P1 wins, and so it will be around this reverse diagonal. And okay, so it's diagonal and reverse diagonal. It's a 2D winning game. So that's pretty much it. So hopefully you can go over the solution and let me know if they find some issues with the code. Thank you for watching the video.